Hi, today I'm going to go over this problem, sketching f of x equals to x to the second over x to the second minus 1 using calculus. This is an interesting problem because it has all the components that are needed to sketch using calculus. Let's get started. Use the guidelines of calculus to sketch the curve of f of x equals to x to the second over x to the second minus 1. We're going to go over the domain, the intercepts, symmetry, asymptotes, intervals of increase and decrease, local maximum and minimum values, concavity and points of inflection, and we're going to sketch the curve at the end. For the domain, we have f of x equals 2x to the second over x to the second minus 1. Now x to the second minus 1 is difference between two squares, which gets factored to x minus 1 times x plus 1. For the domain, we need to focus on the denominator. What makes it 0, we should take it off. So for the domain, we have the following. The domain is all real numbers except what makes the denominator 0, which is -1 and 1. This will give me x cannot equal to 1 because if x equals 1, we're dividing by 0, and that doesn't make any sense. And this will give me x equals -1. So x equals -1 cannot be allowed. That's the domain. So we can't be at -1 and at 1. Intercepts. For the intercepts, x-intercepts and y-intercepts, to find the x-intercept, we let y equal 0. And if we let y equal 0, this becomes 0. And for this rational function to be 0, the focus will be coming from the numerator because 0 over something is 0. That implies if y equals 0, we have x equal 0. For the y-intercept, the second part, we let x equal 0. So if x equals 0, we end up 0 over 0 minus 1, which is 0. So if x equals 0, we end up with y equals 0. So for the x and y-intercept, they're both give me 0, 0. That's this point right here. Okay, that's for the intercepts. Symmetry. Now, it's good to know all the components. As you could see, this is like a lecture video, not just like solving the problem. For symmetry, we know that this is even and this is even. So f of x and f of minus x, they're both the same. Plug in 5 or plug in -5, it's going to give you the same answer, which means the function is even, which means also that the graph is symmetric about the y-axis. That's even functions. You could go back to the function y equal x to the second, which is an even function, and the graph is symmetric about the y-axis. Knowing symmetry is one of the key factors to graph. Asymptotes. Let's start with horizontal asymptotes. To start with horizontal asymptotes, on the left, we have the following. The limit as x approaches infinity and x approaches -infinity of f of x. That's my function f of x. We want to see towards infinity what happens to the values of f of x. The formal way in every calculus book when they start is the following. we have 2x to the second over x to the second minus 1. They're both the same degree, but the focus is on the denominator. The highest degree term of the denominator is second, and we're looking at x to the second. So we divide the numerator and the denominator by x to the second every single term. This is what happens. We have 2x to the second divided by x to the second. We have x to the second down divided by x to the second, and we have 1 divided by x to the second. This simplifies to 2, and this simplifies to 1. So the fraction becomes 2 over 1 minus 1 over x to the second, because this one does not get simplified. Now we could take the limit using the limit rules and apply it to every single term on top and bottom side, as you could see. Limit 2 as x approaches infinity or negative infinity is not going to go anywhere besides 2. It's gonna stay 2. Same thing right here. It's not going to change. It's going to be 1, and the focus will be on this part right here, as you could see. Now we know that 1 over x to the second is graphed this way. This is 1 over x, but when you have 1 over x to the second, you're not going to get any negatives. 1 over x is a graph that goes this way. And it's good to know the basic graphs for limits. 1 over x to the second will be steeper right here, as you could see, and this will flip to the positive side. As x goes to infinity or x goes to negative infinity, the values will go to 0. So this part right here will go to 0. So the final answer becomes 2 over, after you apply the limit, of course, and simplify, 2 over 1 minus 0, which is just 2. So we do have a horizontal asymptote at 2. This is a horizontal asymptote. Let's find the vertical asymptote or asymptotes. To do that, we need to factor the denominator and look for the zeros of the denominator. Now I have x minus 1 equals 0. That gives me x equals 1. And we have x plus 1 equals 0. That will give me x equals negative 1. Now if you have a denominator that has x plus 5 and a numerator that has x plus 5, that is not the same as vertical asymptotes. This will be x equals negative 5, a hole in the graph. That's something else. It's not part of this problem, but it's good to know. So the zeros of the denominator that don't cancel, like the case that we have, in the case that we have vertical asymptotes. So we do have vertical asymptotes at x equals negative 1 and at x equals 1. So we do have vertical asymptotes right there at x equals 1 and x equals negative 1. We have from the first part at y equals 2 a horizontal asymptote. As you could see right there. And that's in more detail. Horizontal asymptote at y equals 2 and vertical asymptotes at x equals negative 1 and at x equals 1. Intervals for increase and decrease. This part comes from the first derivative test, increasing decreasing test. If we have f of x equals 2x to the second over x to the second minus 1, to find the derivative, we used the quotient rule, which is stated on the right side, right here. So the derivative of a quotient like this, we take the denominator and raise it by 2, or the second degree. We put it up here as is, times the derivative of the numerator, minus the numerator as is, times the derivative of the denominator. So let's apply it to our example. So we have x to the second minus 1. We raise it to the power 2. That's the denominator square, as you could see on the right side. Then we go to the top, we write the denominator as is, which is x to the second minus 1, times the derivative of the numerator, which is 4x, the derivative of 2x to the second, minus the derivative of the denominator, which is 2x. That's the derivative of x to the second minus 1, 2x, times the numerator as is, which is 2x to the second. The bottom side is already there, right here. The numerator will simplify. Let's use the distributive property right here. That's going to be 4x to the third minus 4x. And next to it, after subtract, we have a subtract. 2x times 2x to the second will be 4x to the third. Now notice that this cancels this right here. So we end up with negative 4x. Now the first derivative is minus 4x over x to the second minus 1 to the second. This is always positive. This is always positive. And the top part is minus 4x. So we do have f prime of x would be 0 to find the critical points when minus 4x equals 0. That is x equals 0. So when x equals 0, the first derivative, let's use red right here, first derivative value will be 0. And when we have zeros of the denominator, that when x to the second minus 1 equals 0, when x to the second minus 1 equals 0, that says x to the second equals 1 or x equals plus minus 1. F prime would be undefined. So we have derivative will be undefined at 1 and will be undefined at negative 1. Plug in numbers between negative 1 and 0, between 0 and 1, between 1 and 2, or above 1, I mean, and below negative 1, we'll end up with the following. We have a positive values right here. You could take your time and plug in anything below negative 1 in f prime. And you could see negative times negative will be positive. Negative 4 times negative 3, for example, as negative 3 will be positive. The bottom side is always positive. Same thing right here. It's going to be a negative number. To the right side, plug in any positive number, like half or 3 or 4 or 5, you will end up with negative. So we have increasing, increasing, decreasing, decreasing. That says that this point right here is the only point that we have a maximum value. So the graph is increasing, then increasing again, undefined at negative 1, but either way at negative 1 it's out of our domain, if you remember from the first part. We do have a vertical asymptote at negative 1 and the graph is undefined. It's not part of the domain. Same thing for 1. So we have a max at 0. To apply that, we go to intervals for increase and decrease and local maximum and minimum values. So we found from the previous page that the derivative is negative 4x over x to the second minus 1 to the second. This is always positive, the denominator, and this right here, if you have a negative, it's going to end up positive, because negative times negative is positive, and that's what we had earlier. And to the right, it's going to be positive, and it's the other way around. Let's go back. Negative times negative is positive, increasing, increasing, decreasing, decreasing. That's what we had. So we do have increasing on the left of 0. Of course, negative 1 is not part of the domain, and decreasing to the right of 0. So the graph will be decreasing right here, and the graph will be increasing right here. At 0, we mentioned that we do have a local max at x equals 0. And we know from previous slides that the intercepts gave me 0, 0. So we have local max at the point 0, 0. So this point right here is a local max. So the graph is going to go like this, right here. That should do it for part E and part F. For concavity and points of inflection, we need to find the derivative of the first derivative. In other words, finding the second derivative. Again, we're going to apply the quotient rule on the right side and fill in the places right here. So we take the denominator, which is x to the second minus 1 to the second. We're gonna square it. That's for the denominator. That's why I have it all here. We're gonna square it. We're gonna keep the denominator as is and follow. So let's finish it. This right here will be to the second. We keep the denominator as is on top to start with. So x to the second minus 1 to the second. That is the denominator as is. I do have a second degree. As you could see, that's the denominator as is. Now the numerator will be, we need to find the derivative, which is a minus 4. The derivative of minus 4x is negative 4. Next, we have, as you could see right here, the numerator times the derivative of the denominator. The numerator is minus 4x, so I'm going to write minus 4x, times the derivative of the denominator. 2 goes up front, x to the second minus 1 to the power 1, using the chain rule, times the derivative of what's inside, which is 2x. Now, notice that we have this part right here, x to the second minus 1, repeats also right here. So instead of multiplying everything, let's take it out as a common factor. And that's going to go right here. We're going to take one of them, because that's the greatest that we could take. I know the first part has 2, as you can see right there, but we only could take 1 as a common factor. So we have x to the second minus 1 to the first. From the first part, we have minus 4, and we have x to the second minus 1. Just one of them left. The second part, when we take x to the second minus 1 out, simplifying everything, we have 2x times 2 times negative 4x, and that will give me minus, let me use the marker here to show you. We have minus times minus, or negative, will end up positive, as you can see right there. We have 4 times 2 times 2, that's This is times, not subtract. That will give me 16. And we have x times x will give me x to the second. So we have 16 x to the second. Now we could go back and say one of this will cancel one of these and will leave me with 3, as you could see down. So the top part is this right here, what stays with me, which is going to go right here. Now I have minus 4 times x to the second minus 1. That's minus 4 x to the second minus 4 x to the second, and minus 4 times negative 1, which is positive 4 plus 4, and we have 16 x to the second. Notice that the first term and the last term, they are alike, so we need to combine them. 16x to the second minus 4x to the second will be 12x to the second, and I have plus 4. This is what I have so far, and that is second derivative. Notice that the numerator is 12x to the second plus 4, which is always positive. And we need the sign of the second derivative. That's the line down below. Here, second derivative will be 0 if x to the second minus 1 is 0. But that is x equals negative 1 and x equals 1. So here, the second derivative is 0 at, let's say, f double prime will be 0 at x equals 1 and at x equals negative 1. However, we need to be careful. This is not going to be accepted because the domain was all real numbers except 1 and negative 1. So negative 1 and 1 are not part of the domain. So we have to check around 1 and negative 1. We end up with looking at x to the second minus 1 sign, but x to the second minus 1 from here is actually a graph like this instead of doing the algebra steps. That tells me that this value x to the second minus 1 will be positive on this side, positive on this side, and negative down below. So it's going to be positive right here, positive right here, and negative right here. That says that the graph is concave up to the right of 1, concave up to the left of negative 1, and concave down between negative 1 and 1. 1 and negative 1 are not part of the domain, so they are not inflection points. Just because they're not defined. The function is not defined at negative 1 and 1. So the graph will end up concave up to the left of negative 1, concave up to the right of positive 1, and concave down between negative 1 and 1. I know it's a lot of steps, but as you could see, I try my best to write less by having enough notes ready to go. That's one reason why I'm using the PowerPoints or the slides instead of using the whiteboard. For the whiteboard, all these writings, all these steps with the previous slides will take a lot of work. Now we come almost to the end. Use the guidelines of calculus to sketch the curve. To do this, the limit concept right here, close to the vertical asymptotes, 1 and negative 1, is more explained in pre-calculus books, the way I see it. Let's take a look at this. I have the vertical asymptote x equals 1 and x equals -1. We're going to approach 1 from right and from left. From its right and from its left. I should graph it right here. This is my x-axis. Then we're going to do the -1 from right and left. As you could see from this slide, that I take my time to write almost everything instead of writing things like this on the whiteboard. Writing all these on the whiteboard, that's part of the problem. That has too many steps, as you could see. Will take a lot of time. And it's neater and cleaner on the slides, as you could see. That's why I call my videos lecture videos, mainly. Let's go back to the problem. To approach 1 from the right, we're going to factor x to the second minus 1, which is the difference between two squares, to x minus 1 and x plus 1. Now when you approach 1 from the right, it's like 1.0001, something like that. This is going to end up 2, like 2.0001. That 2 cancels this 2. And x to the second becomes 1.001 to the power 2, which is like just 1. The only part that is different and we need to pay extra attention to is x minus 1. X minus 1, think about it like 1.001 minus 1. That's going to end up positive. And that's the main part right here. So you need to think what's going on with the following. I have this right here is going to end up positive. And that's the main part that we need to stay focused on. Let's keep going, since I am looking at this part right here with the same portion, approaching 1 from right and left. When you approach 1 from the left right here, you're looking at point 0.9, for example. Well, 0.9 or 0.999 plus 1 is going to be 2, and that's going to be 1, and that's going to 2. This cancels this, and this will go to 1. The only part also, one more time, is this right here. If you think about this and you are less than 1, that's 0.9 or 0.99. 0.9 minus 1 is going to end up negative. And that's our focus. Let's go right here, highlight it, and write negative. So stay in focus with the first part, then we'll go to the second part. Next. So the limit of 2x to the second over x minus 1 times x plus 1 on the first line becomes 2 times 1, 2 times 1, and this is positive, as we said, times 2. Simplifying this, that's almost like 1 over x, but 1 over as a fraction. We need to think about the denominators are getting to be too small. 1.001 minus 1 is 0.001. It all goes back to 1 over x and how 1 over x behaves as a graph when the numbers gets too small. If it gets too small but from the positive side, you're going to go to infinity, and if it gets too small from the negative values, it's going to go down to negative infinity. It all goes back to 1 over x. So this right here will end up positive infinity, and that's the main part. So as x approaches 1 from the right, we're going to go to positive infinity. Second part, when x approaches 1 from the left, as we said, we have a negative highlighted right here, and we end up with this goes to 1, this goes to 2, so we end up with limit of 2. Of course, this is like a limit right here, and this is like a limit also. 2 and 2 cancels, so end up with 1 over x minus 1, and that's going to be negative small amounts, kind of like 2 times 1 and 2 right here, and this right here would be a very small negative number. Applying the limit to that, that will give me negative infinity. So we're going to go down this way to negative infinity. Let's go with the second part as x approaches negative 1 from right and left. So here we go. When x approaches negative 1 from the right, somewhere right here from the right. So we're looking at like negative 0.9. Negative 0.9 and negative 1 will be negative 2. Negative 0.9 plus 1 will be a very small number, which is negative. So this is now what happens. This becomes like negative 0.9 plus 1, which is a positive value. That's going to be a positive. Let's highlight this one right here, and we'll also highlight this to get it ready. One more time. Think about it like negative 0.9 plus 1. That's a positive value. Okay? 1 minus 0.9 is 0.1. So we are looking at very small numbers, but positive. Very small numbers, but positive. On the other hand, when x approaches negative 1 from the left, this right here, we're looking at approaching negative 1 from the left. When you approach negative 1 from the left, we're looking at negative 1.1. So when we have negative 1.1, negative 1.1 plus 1, that will end up a negative 0.1. Negative 0.1. Very small number. Thinking about the behavior of 1 over x. Negative numbers will give me as a fraction to negative infinity, of course, if the rest cancels, and gives me the behavior of 1 over x. Going back to the problem, we have the following. We have 2x to the second becomes 2 times 1. That's like 2 times 1. And this right here becomes negative 0.9 minus 1. We'll get close to negative 2. Same thing right here. I have 2 times x to the second will be like 2 times 1. And approaching negative 1 from the left, like negative 0.01 as a final answer, as you could see right here, that will give me a negative value. Let's go right here. Negative 1 from the left. Negative 1 from the left will give me a negative value, and this right here will give me close to 0. Close to negative 1.1, negative 1.1 minus 1, which is negative 2. So same idea like on top. This is like negative 2. So we are ending with 2 times 1 over negative 2 times a very small amount, but negative. And on top it's going to be 2 times 1 over negative 2 times a very small amount, but positive. So the first one will give me a behavior of negative infinity, and the second one will give me negative times negative at the bottom side. It's going to give me positive infinity. Approaching negative 1 from the right, we're going to go to negative infinity, and approaching negative 1 from the left will approach positive infinity. A lot of details, as you could see. Finally, To summarize what's going on, we have the domain, all real numbers, except -1 and 1. Intercepts, we ended up with 0 and 0. That's this right here. And symmetry, we have f of x equals f of -x. That's called even in math, symmetric about the y-axis. Asymptotes, it's already on the graph. We have horizontal asymptote at y equals 2, and we have vertical asymptotes at x equals 1 and at x equals -1, as the graph shows. In terms of increase and decrease, we came up with increasing, let's see, first derivative test. First derivative test was at 0 equals 0, undefined at 1, and undefined at -1. And we ended up with increasing, increasing, decreasing, and decreasing. Increasing, increasing, decreasing, decreasing. We have a max or local max at 0, which is actually the point 0, 0. That's local max at 0, 0. Let's write it down clearly. We have local max at 0, 0. We don't have a local minimum values. Concavity and points of inflection. Points of inflection, we found that the graph is concave up on the left of -1 and concave up on the right of +1 and concave down between -1 and 1. That's concave up, concave down, and concave up. And also the limits that we had getting close to the vertical asymptotes from the previous page. These are not inflection points because the domain does not have the -1 and 1. I know it changes direction from concavity right here, and it does also right here, but those are out of our discussion. They're not inflection points, and they're not part of the domain. To sketch the graph, we know enough now. The graph is concave down and approaches -infinity as you get to 1 from left and to -1 from right, and also concave up to the right. And we know that it gets close to the horizontal asymptote, y equals 2, and goes to +infinity to the top part. And that is the graph. Now, of course, it's a quick graph by hand, but here's the detail. That explains it all. As you could see, this is a function or an example that covers all points of interest using calculus concepts: inflection, increasing, decreasing, and so on. That should do it.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.